seeing is believing. So now is no more who put it in the microscope and really showed that such a beautifully layered material with all slabs, etc., of uniform dimensions, no defect, etc., was shown to Superman, and that was a publication in Journal of American Chemical Society. Okay, go to the next one. Now this is a schematic model set here again. So I don't want to prolong beyond this point. I think I will maybe go a couple of things. Let us what is the next step? Go to the next one. Yeah, go to the next one. Next one. Subsequently, we did a lot of things with perovskite. Go to the next one. Next one. Next one is all layered perovskite. We did a lot more metathesis. Recent times also we did metathesis. Go to the next one. Keep on going. Metathesis, PA2O2, again another Jacques paper with Ramanujan, with Ram Seshadri. Recent times we did metathesis of this. I think will be of some interest to people here. Thirumal is working on PhD, MD, PA209. We have found out the metathesis route, one-part metathesis route for preparing this kind of dielectric ceramics which are useful in application, etc. Go further, please, and keep on going now. So don't need a whole lot of things we have done to prove all these things. Yeah, stop. Rutile is another well-known oxide structure, well-known structure. And in rutile, we have modified the rutile like this. We have replaced 2/3 of the titanium in rutile oxide with iron and tantalum. Of course, we did a whole lot of compounds in order to find this one example. And there is a big interest to find relaxer fullerenes without latex. And this is one thing that we have heard. FETI here was saying that that was in advanced materials in the communication. Sometime back, Dr. Tyagi from BRC helped me to fix all the properties and so. Just want to show you how simple structures like TiO2, with the imagination, you can create new functional materials. Go to the next one. Yeah, these are the other things, properties, etc. Further, keep on going. Yeah, these are earlier one. Again, yeah, stop. Before you come, go back. Yeah. See, no, yeah, go one step back. Yeah. See, CrO2 is a magnetic material. Earlier we used to use CrO2 tapes, now we don't use it. But still it's an important magnetic material, 100% the charge is polarized, and so on, all kinds of attributes are there for this CrO2 material. Unfortunately, you cannot make the material CrO2 under ambient conditions because the oxidation state is 4+. Conventional oxidation state for chromium chemistry, you people know, 3+, they do 3+, 6+, dichromate. Chromium 4+ is very difficult to stabilize under ambient conditions. We did stabilize this material. I was at DuPont and learned DuPont holds a patent of this high temperature, hydrothermal and all that. So when I came back to Bangalore, we did a simple reaction of taking CrO3, mixing it with ammonium iodide. You can use ammonium bromide also. First heat it at 120 with the exact required stoichiometry you have to put so that chromium 6 is reduced to chromium 4. All other things are gaseous product. First step 150, second step 190 in a closed tube. Go to the next one, please. And you see the first step will use an X-ray amorphous material. Second step it crystallizes into beautiful ferromagnetic rutile structured CrO2 with the expected ferromagnetic and metallic properties. That was done by Ramesha subsequently. Okay, just again, what I wanted to impress upon him is with the imagination and knowledge of chemistry, you can come up with new solids and also new routes for some of the important solids. Now you have to go forward to the last. And this is the conclusion. Again, you can read it, what all the things you can do. And go to the next one, please. I just want to focus attention for 2 minutes I will take. Everybody recognizes this is Mona Lisa. It's one of the biggest forms of human creativity. When you go to the Louvre Museum in Paris, everybody will be asking for where is Mona Lisa, where is Mona Lisa. Thousands of other paints are there, but still people are interested in Mona Lisa. So that is the worldwide attention this Mona Lisa painting has got. And that was created from an ordinary piece of canvas by the famous Leonardo da Vinci. Go to the next one. This is a piece of marble that lies everywhere. And what Michelangelo did, that wonderful thing of creating Peter on a bit, that is really carrying the dead Jesus Christ's body. So these are important pieces of human creativity in the realm of arts. When you come to science, the kind of materials that we make in the laboratory, actually if you go to the laboratory, they are not at all attractive. Nobody would like to take a second look at it, including ourselves. But they are useful. That is why they have some useful properties. That's why it is important. So the kind of creativity in making ordinary chemicals which are available in the bottles and elsewhere, by putting together imaginatively to create useful materials, also is an important task. That is where the highest form of creativity of scientists is involved. And this is the message that we want to convey for the last one. That creativity is very important. You call it innovation, you call it creativity. A whole lot of people have helped me. At the end of the day, I have to remember all of them. The names that I have listed on the top, including Professor Rao and other people, they are my mentors and supporters who have supported me in this venture in my journey of nearly 40 years in this field of structural chemistry. These are some of the wonderful students that I had with me, and they are tirelessly working. It is very easy for me to take a piece of paper and write down some reaction and say, go to the laboratory and perform. But those people tirelessly, day in and day out, with eager listening, they have toiled in the laboratory to produce some realities that I have presented. I am thankful to each one of them. And some of them are here. Ramanan is here, I think. Uma is there. A.K. Ganguly is there. Vijayaraman, Kanapati, Nagarajan, Subbanna, Shukla, Seshasri, K.V. and Aditya. And a whole lot of, next one please. Those are the printing agencies who supported me. And some of them are even there. Thank you very much for your time.
Thank you, sir. Thank you so much. And as I mentioned during his introduction, that he is a living legend. And as per his words during his lecture, that seeing is believing. And I trust that you all believe that he is in true spirit is a living legend in solid state chemistry. Thank you, sir, once again.
Now we have come to an end, but before that I would like to say something, that the beauty of the Taj Mahal is appreciated by everyone, and all praises to Emperor Shah Jahan. But no one knows the effort of those whose contribution remained unseen, hidden and unnoticed, which made it the greatest wonder of the world. This conference is not an overnight dream and has emerged through the hard work and the sweat of many people who came from various backgrounds and committed to support and to make this conference an impressive and successful event. Now I request my colleague and one of my very dear friend within the Department of Chemistry, Dr. Taqir Ahmed, who is also the convener of the symposium, to please come up to formally propose vote of thanks to all those without whom this conference was not possible. Dr. Taqir, please.
Thank you, Saika. Professor J. Gopalakrishnan, our honorable keynote speaker, Professor Khalil Ahmed, Dean Faculty of Natural Sciences, Professor B. Vishwanathan, Professor Sundar, Professor Patra, Professor Kusrestha, Professor Al-Shihri and Professor Al-Shahmi from Saudi Arabia, Dr. Ito from Japan. Distinguished dignitaries and invited guests, my dear colleagues and students, a very warm good morning to all of you. It is my pleasure to deliver the vote of thanks on this occasion of 7th National Symposium and Conference on Solid State Chemistry and Allied Areas, to all who have tried to make this event in a majestic way. First of all, I would like to thank Professor Safuddin Soz for accepting our invitation to be the chief guest and agreeing to inaugurate the conference in spite of his busy schedule. I am extremely thankful to our Honorable Vice Chancellor Janab Najib Jang Sahab for the kind permission to organize the conference in the university, and with his generous support, the things became manageable. He always motivates us by his blessings and extraordinary support. I am really thankful to our Honorable Pro Vice Chancellor Sahab, Professor Rashid, for accepting our invitation to preside the inaugural function. This conference was not possible without the help and support of the Indian Association of the Solid-State Chemists and Allied Scientists, that is ISCAS. I am really thankful to the association for showing their trust on us and especially on our university by accepting our proposal for hosting the 7th ISCAS conference at Jamia Millia Islamia, as there were many universities who had submitted the same proposal. I express my sincere thanks and greetings to Professor J. Gopalakrishnan for his gracious presence at Jamia Millia Islamia. I am extremely thankful to you, sir, for sparing your valuable time in your academically very tight schedule and accept our invitation not only to be the keynote speaker but also to agree to be with us till the end of the conference. Thank you very much, sir.
Good afternoon, my dear friends. Before I take my 30 minutes, I will take 1 minute and thank the organizers for giving me this opportunity to talk to you on a topic like this. When the organizers asked me to talk on this symposium, I was wondering what I will be able to talk to you in the solid-state chemistry. Basically, what I am looking at it is only the scratching the surface. The process that takes place on the surface is what I have been looking for some time. I have not looked for properly, but I have been trying to look at them. Now, when I was looking at them, I found that the reactions that are taking place on the scratching of the surface is mostly the reactions that are also taking place on the solids. In the morning, you have been hearing a lot of things about what is the solid, what is this thing, why this is happening, and all those things. For example, in the one of the cases, Professor Gopalakrishnan was talking to you, two important slides, at least two important slides from my point of view. He was showing you that when you mix two substances, there is an enormous energy is released. That is one slide he showed you. Another slide he showed you was that when you wanted to prepare a zeolitic material, he showed you all kinds of exotic, non-native structures. All the non-native structures are formed. After that only they are going to the native structure. So now catalysis is basically taking place on non-native structures. Now, the same logic is holding good for the solids. So we will just quickly go through them. Essentially, if you look at it, why the solids are so important is that you will not be able to realize it, but this is the fact of life. I don't want to go into the history or the period of that, but every decade, if you look at it, if you carefully look at the decade of every decade, maybe 50s, 60s, 70s, whatever decade you look at it, a material came, because of that only all other scientific developments happened. For example, I will tell you, then only you will understand. The material of nanomaterials were there, that is why all the types of EMs, okay, two alphabets you combine, put another alphabet, M, A, AFM, whatever, so you put all the 26 alphabets in whatever combination, there will be one M. Okay, just like our I, T, T, V, T, you put I, B, T, N, T, whatever you want, you will make a technology. The same way, the scientific developments have been based upon the materials that were thrown out every decade. So now, how these materials came about is the question that I was asking myself, how these materials could be synthesized, how these materials were coming. Maybe because of the demand. Okay, for example, in the 60s, they wanted all kinds of entertainment. That is why semiconductors came. In the 80s, all of us fell sick somehow or other. So therefore, the material of zeolites came because the pharmaceutical industry was demanding. Then we became greedy. Therefore, we wanted to not to spend any money. Superconductors came. So like that. Okay, you can see like that. Every decade there was a material thrown because of the demand of the people, and the material thrown gave us all the kinds of developments in physics, chemistry, biology. As a matter of fact, today, why are you looking at the nanomaterial is you are now forced to understand life. So therefore, probably we are thinking, because we are always a blind man in the, as far as life is concerned, so we are thinking that this nanomaterials may throw something on their life, because life is essentially centered on sensing. You are sensing the other man, you are sensing the other man's feelings and other things. So the nanomaterials are one of the set of materials which can be very good sensors. At the moment, I'm not going to talk about all of them. How these materials have been coming out is because of the active centers that are created. Why are we looking at the active centers today, you will ask me. That is the beauty of the material science, or materials themselves. Materials, you take a material and go on reacting it till the last 1% or last molecule reacted, the concentration remains 1. So therefore, you cannot, all the kinetics that we are teaching in the classroom does not obey here. The total kinetics, the dynamics of the process is controlled by dimensionality here. So therefore, the moment you are looking at a dimensionality, it all depends upon how your mother has fed you. So you can be a vertical direction or horizontal direction or both directions put together, whichever way. So the same way the materials also has a very great dimensionality. And when you make the materials in a dimensional fashion, some dimensions are, for example, 1D materials may be important for some reason applications. 2D materials will be important. Now what we are looking at is that the materials that are present on the surface where the growth is occurring. Because all this process is taking place by the nucleation and the growth mechanism which Professor Gopalakrishnan was talking to you. So now the factors that contribute to the material science is essentially dependent upon how will I nucleate and how will I grow them. So therefore, I have already told you that the dynamics of the process in the material science is totally different from the dynamics that we have learned. It is not a concentration-dependent term. It is a material-dependent term. Concentration remains throughout the kinetics 1. Okay. So how are these in these materials? They are initiated. There can be a variety of questions that we can go on asking. So essentially, I looked at how this concept of the active centers came. At least for the surfaces, it came from a postulate by Professor Taylor in 1925. He was looking at the surface and looking at exotic coordinations. Okay, exotic coordination means because the surface atoms are less coordinated than the bulk atoms, therefore he was telling that the lack of coordination completion is what is the active site. But he did not tell us whether it should be 3-fold coordination, 4-fold coordination, because all of them are incomplete coordination. So therefore, which one of them is going to be the situation, or is the active site is beyond this coordination, is what we have to see. So now, in the last 20 years, if you look at it, in a surface process, I tell you, this is same surface process. So if I were to make a bulk material, it takes the bulk material. So surface process, the active site, as I told you, because of the lack of coordination, can exist a priori on the solid. But it is not true. Active sites can be generated at the call of the molecules. The inactive sites can be turned into the active site. Okay? That is what we were looking at. Non-reactive substance, when you put it in another reactive substance, it becomes reactive. So there are varieties of the active sites that can be possible, but these are the three different types of active sites that we have 20 years back. But today, we have many more active sites. We will see later on. So therefore, essentially, what is left for us is how we will be able to identify these active sites. After having identified these active sites, how will I optimize the number of active sites? This is applicable to the surface process as well as the growth of the bulk material. How will I manage to keep them in that state? Because Dr. Gopalakrishnan has already told you, we will also look at it. Many of the materials that we are talking about are materials that are relevant for us are the metastable states. That is what I am saying is that they are capable of exhibiting non-native structures. Native structure is what is thermodynamically possible that Gopalakrishnan has already told you. So now, the bulk may be native still, but the surface can be non-native. That is why the surface is very reactive. So therefore, the coordination and saturation must be understood in a different language now, that the surface structures are non-native in nature. Okay, then what non-native is active and what non-native is not active, we will see. or two non-native structures can be giving rise to two different activities. So therefore, we should work for looking at all this structural configuration and then look at it. Essentially, what we have been doing in the past is, somehow or other, the Gopalakrishnan also was telling you, somehow or other put the physical chemistry concepts or some concept, we will not worry about it, physical, organic, inorganic, some scientific concept we put, some heat of formation, which denotes the whole of the bulk of the material, then you correlate it with some activity. Activity can be put any parameter you want. It can be temperature, it can be the rate at a particular time, temperature, whatever it is. So therefore, the variety of correlations have been done. Okay, here it is the heat of formation versus the activity. Here is the lattice constant versus the activity. Variety of them. Okay, the percentage D character versus activity. Variety of them have been done in the past. Now, this type of correlations only led to the Nobel Prize in the 2007 to Ertel, because of he could rationalize all these correlations and work out the mechanism which was done one century ago or 100 years ago by Fritz Haber, ammonia synthesis. So now, if I were to look at it, what he did here, I hope I am able to see the figure. What he did was, here he put some kind of a bond strength. Okay, in the x-axis, the bond strength is put at various planes of the surfaces. Then on the y-axis, he put the activation energy for the activation of nitrogen. Because in the ammonia synthesis, the activation of nitrogen is what is more important. So now he could come up with the optimum configurations a priori without doing an experiment. Then they went about looking at that experiment, looking at the you can see here, variety of non-native structures for the same metals are exhibited at the surface. Whereas in the bulk, it may be an FCC metal or a BCC metal, but at the surface, the structure may be different. When it is different, definitely it will be active. We will see that. Now, you will ask me, how do you know that the surface is different in configuration with respect to the bulk? You take a alloy. For example, I am sure you would have had a coin, put it in your purse, forgot about the coin for some time. After some time, you opened the purse, you would have seen a hole in your purse, plus the coin has tinted. What has happened? Coin is an alloy. So therefore, one of the metals in the alloy segregated to the surface because of the call of the oxygen or moisture or whatever it is, atmospheric conditions. Therefore, that came to the surface. Even though the bulk composition is 50-50, the surface composition may be 80-20. So therefore, it is already known to us that the surfaces of materials have to be different from the bulk structures. Even if it is if you take a multi-component system, we have done many experiments. Multi-component system also, the material that has a lowest surface tension will segregate to the surface. So therefore, this concept that the surface morphology or surface morphology is not correct, surface organization with respect to the bulk organization is different. That is why the growth, nucleation, and all those things take place at the surface and grow. So now, what is the role of these non-native configurations? That is what we want to look at it. Definitely on the surface, the non-native configuration has a role, but it is also may have in the preparation of the bulk materials, but I am not going to deal with that now, because I wanted to bring to you a totally new way of looking at these nanomaterials, because this today we are supposed to talk on that. Why are we considering this? I have already answered. Because today we are synthesizing many nanomaterials. I will show you many nanomaterials that you are exactly looking at it. You will have the same number of atoms, but in two different morphologies, in two different configurations, in two different orientations, and two different reactions. That is possible. Now, what is happening here is, that is why people are talking about the nanomaterials is so important. Because in any of the reactions that we think, we are worried about how we will be able to optimize our selectivity. Selectivity means that the desired product has to be obtained to a maximum extent. I will show you one example at least at the end. Now, when we do this, we must have some governing principles. Okay, I will demonstrate this, but only one governing principle. Okay, because time is the factor. I hope you know, today's major endeavor in science itself, especially for the chemists, is how will I convert carbon dioxide into value-added molecules. Water decomposition is important. I don't deny that. Don't think that I'm saying only this. But this is a major endeavor because all our politicians sat together and talking about climate change and all those things. Okay? So how will I do this activation of carbon dioxide? So nature is doing it every second, Avogadro number of molecules. But whereas you give me a CO2 molecule, for my whole life I will convert only one CO2 molecule. Whereas nature is doing every hour about an Avogadro number. In this time, I must tell you, many of us may not know what is this Avogadro number, including Avogadro. Because we know Avogadro number, 6 into 10 to the 23. But you tell me, you start counting to 1, 2, 3 and reach 10 to the 23, then only you'll know what is the Avogadro number. Otherwise, because we do not know, it requires at least 400 years for you to go to the 10 to the 23. So unless nature is going to give you 4 births, and nature is going to give you remembering what you did the previous birth, you do not know Avogadro number. That is why I said Avogadro also did not know this, because Avogadro also lived only one life. So anyway, I am not talking about Avogadro number here. What is the peculiarity about the carbon dioxide? Okay? In the case of carbon dioxide, immediately you will say, I know what is the carbon dioxide. What is the problem? That is not a problem. You take the angle OCO, because you see, the moment you put the carbon dioxide on any surface, the reaction will take place on the two oxygens that are present at the end. But what we want is, the activation has to take place on the carbon and oxygen, not 2 oxygens, only one of them. Then only I will be able to control the carbon dioxide into formaldehyde, formic acid, methane, whatever I want, okay, whatever way I want to use it for a value-added chemicals. Now, if I have to do this, I have to necessarily change the bond angle. OCO bond angle is 180, okay? But if OCO bond is not 180, then it will be more reactive, because it is strained. So now if I were to do this, I have to attack the carbon and oxygen. Then only I can bend this molecule. So now if I were to look at the carbon and oxygen in the carbon dioxide, it is in an angular disposition. Therefore, I need a site which is at the tip of the step, and another site which is at the bottom of the step. Then only I will be able to do this. So I hope now you realize why stepped surfaces are important. This is I told you this is only one example. There can be many examples where the bond angle is going to be manipulated. That is why your teacher, my teacher, everybody has told you tetrahedral angle, and then a deviation from tetrahedral angle. That he will go, it is lone pair, or all kinds of things he will say. Essentially what they are telling you is, the moment you are changing the bond angle, the molecule is reactive in the way in which you want to be reactive. But it can be also in the non-selective way. Okay, but if you change the bond angle in the way you want, or in the direction of the product that you want, definitely you will be able to achieve 100% selectivity. This is with respect to CO2, but many other things are possible. So therefore, I am not going to repeat all these things. So this is what nature is capable of doing. Enzymes are doing that, because that is why your teacher and my teacher told me lock and key mechanism. What is mean is, when you put the key, it is getting fitted into various angles at the lock hole. The same way, the molecule also, if it is capable of getting locked up in the fashion in which the bond angles can be altered, I will be able to do this. For example, if I cannot, let us assume that I take carbon dioxide, I cannot change the 180 degrees, I cannot get any selective hydrogenated product. It is not possible. Okay, it may be too much to say. In the future it may be possible, but today's knowledge that is available to me shows me that it is not possible. That is why many of us who have tried to take carbon dioxide to reduce it, we are only successful in electrochemical means. Because electrochemically, the electrodes are capable of exhibiting these type of exotic sites. Other electrodes will not be able to do this. So now how will I modulate this? There are variety of questions that we have to answer, but I am not going to talk everything. So if surfaces are going to adopt non-native configuration, is there any relationship between the native configuration of the bulk and non-native configuration of the surface? For example, let us assume that I have a FCC lattice is the bulk. Can I get a BCC configuration, not lattice, okay? BCC configuration on at the surface. If the bulk is going to be FCC, can I say surface can be BCC? That type of predictions, is it possible? Okay. What factors control the sustaining of one of these non-native? It is not enough if I have a non-native structure, I have to also sustain this non-native configuration at the surface. Okay. So one can go on asking variety of questions, but we don't have time. So now a little bit, only one of them, non-native configurations are metastable states. As Gopalakrishnan was telling you, all the devices that we are using is non-native configurations. And we will not demonstrate it, but it is already known, and he has already shown few projections on it. It is possible one will have more than one non-native configuration on the surface. It is not necessary that only one non-native configuration will be there. Among these possible states, only one of them may be active for a chosen reaction. The preferential non-native configuration is controlled by the nucleation and the growth kinetics, just like the solid-state reactions. The protecting agents with the functionalities control the kinetics of the nucleation. This is why when you are synthesizing a nanomaterial, you are putting a capping agent, you call it anyway, anchoring agent, whatever you call, it doesn't matter. What you are doing is you are bringing the atoms in a non-native configuration. That is why you need, when you are bringing an atom in a non-native configuration, you have to stabilize it. Therefore, you are trying to stabilize it as though you are doping it by putting a capping agent or nucleating agent, anchoring agent, whatever you are talking about. And growth, and though other factors like initial concentration and temperature in the nanomaterial synthesis is important, but this is the one that controls the non-native configurations that are being adopted. How do you know this? Is the question, next question you will ask me. So therefore, there are variety of passages, we will not go into it. We have done some amount of a density functional theory. I am not going to bore you with all the quantum mechanics. And then looked at the possibilities of native and non-native bulk structures differing, surface structures differing from the bulk native structures. So computations suggest that the lower surface energy of non-native structures always facilitates the stabilization in the early stages of the growth. Early stages. Ultimately, it will go to all of them will go to the native structure. But in the early stages, if you look at it, it appears to be the non-native configuration appears to be the low energy path. Therefore, as the growth occurs, the non-native structures take place. Then when you give the infinite time, when the equilibrium situation is taking, then it is. But you are not allowing any equilibration to take place in the nanomaterials. As I told you, you are putting all kinds of capping agents and everything, you are freezing them in the non-native configuration. So therefore, just in the compound semiconductor, in these calculations, we have only looked at the semiconductor, oxide semiconductors. So the transition pathways between non-native and native structures involve planar or non-planar depolarized layers, and the growth conditions have significant effect on the stabilization and growth of the non-native structures. The findings have got some relevance. We will not worry about it. So this is how we went. So quickly looking at it, I will take only one or two examples and show it to you where these non-native structures are important. Okay, because in the morning itself, Gopalakrishnan showed a whole lot of list of all kinds of materials. But out of that, I am only going to take one material. One material means one material applicable in one area, energy conversion. That's all we are going to look, because that is all with the time that we have. So now, just now I told you, water decomposition is a very major reaction, and the same fate, just like my inability to convert the CO2, the same inability exists with all the scientists in photoelectrochemically decomposing water. Okay, by other means you can decompose water, but that is all not possible because energy is not gained. So photoelectrochemically, if you are going to decompose water, the fuel value that you are attaining by separating hydrogen and oxygen, the amount of energy that put in for this process is a kind of a balance. You will be able to get some net energy. So therefore, photoelectrochemically, we must decompose water. What is the state of photoelectrochemical decomposition of water today is the question that we are asking. Just for the youngsters, laboratory-wise, it will be around 20%, 22% if you have a very, very, very complicated electrode system. I will tell you in a minute what is meant by complicated electrode system. Whereas, when you want, that is no use. Energy is not a laboratory exercise. Energy is for the common man. I have to produce for the common man. It is not enough if I see you on a hydrogen bubble. So therefore, if I were to do this in a commercial process, it is not even 1.1% or 1% like that. Okay, I have to talk about 100 times less or more than that. So therefore, that is the reason why we are looking at this. So is there is a possibility of making this photoelectrochemical decomposition of water? If I were to devise suitable electrodes, is it possible? Then sometimes I told you, we are also, since we are looking at the catalysis or surface processes, we have to be worried about what is the product that I am getting. Okay, I will, for example, in the pharmaceutical industry, for example, I want in the pharmaceutical industry, there will be a D and L or R and S or whatever it is. Okay, optically active isomers, one will be a medicine, another one will be a poison. Therefore, this type of selectivity is required. I want only the medicine and I don't want the poison. So this type of selectivity is required. How will I promote such selectivities? Okay, if time permits, I will show you one of the two other examples. Because up to now, our organic chemists have been telling us, organic chemists means we, okay, we are also organic chemists, pseudo-organic chemists if you want. What we were telling is there must be an asymmetric center already in the molecule, then only the asymmetric induction can take place. That is not necessary. If I were to be making a material which has lost its center of symmetry, that type of force itself will be able to induce asymmetry in the molecule. But at the moment, we are not able to get a long-range, non-centrosymmetric porous architecture. If we can get it, then it will be possible to make an asymmetric synthesis. But anyway, I am not going to talk about it. Why are we not able to predict the possible non-native forms on the surface? That is, many more questions are there. We will not go into all of them. Do we have some clues? The clues must be